But I'm curious about the instructions. You mentioned very important example in chips. You don't have this luxury to
Yeah,
test for many years.
yeah.
So how do you see the relationship between the structure, maybe how to optimize the structure and design this new material? How you figure out I need this new material, and that's what is missing. Can you give an example for that? How the relationship between morphology structure and new material?
Yeah, excellent question. So one specific problem faced by Intel and the entire industry in
Yeah.
19, almost starting from beginning, but in 1990s, a class problem was made very clear to me. So it was about adhesion, adhesion between different materials. So when you make a chip, you need to adhere maybe a ceramic to a semiconductor and a metal to that ceramic, right? Many, many layers. Right? You need to have an integrated structure, right? So then the adhesion become important, right? Otherwise, you can have debonding. So adhesion, so today many people say, oh, I do ab initio calculations. After so many decades, that approach is still a failure. So it's hard to do interfacial adhesion. Because adhesion is not a property of a given material. It's a property of at least two materials and also how you process it. So during the adhesion process, maybe you have oxygen, maybe you have a nitrogen, a different pressure, just so many variables, temperature. So it's a process variable, right? So now the problem was the following. So when Intel in those days, they said, oh, I have a new chip. I need to develop a new chip. In this new chip, I introduce a new material A into the structure because it has extraordinary low K dielectric at that point. Low dielectric constant. Has nothing to do with mechanics, but it's a new material. Need to adhere well. We had no experience integrate that material into the chip. That's the problem, right? So they're, how do I learn about this? They already knew computation is hopeless. Just never get any useful result to this day. So my computational colleague will be upset, but I need them to show evidence that was useful for this problem. It's not. All right, so then what Intel did was test it out. Oh, okay, I have this new material. Let me put this material on this other material, turn the oxygen knob. Here's how I process so many minutes, so many seconds at this pressure, and then see how it fail or not. That became a problem. So when you just deposit film, think about this film could be, 100 nanometer. The film is so thin, it doesn't have much load. So nearly everything you put on top of it doesn't really fail. So how do you know it fail or not? You need to build whole devices. Now you have a layer upon layer upon layer. These other layers will apply load. So how do you know how much load? Because when you turn on computer, there's a temperature change. So in order to simulate that temperature change give you thermal stress. So the industry will do thermal cycle test. So thermal cycle test for 3 months. And you have the report. Your interface works or not. So then the industry colleague said, I only have 18 months. I need to turn out a product. And each knob I turn, you need to report to me after 3 months.
Yeah.
Whether that knob is correct or not. If a knob is correct, great, 3 months. Knob is wrong, do I do this again? Another 3 months? You see the problem? Your feedback time is too slow for you, specific for this problem.
Yeah.
Just because you need to build a whole structure and the way you apply load is doing thermal cycling. So then how do you do this? How do you do this? So the solution, it turns out I only played a minor role in ultimate solution. I was involved in the beginning, but the crucial role was played by this colleague at Stanford. Rainer Dowsker. He was my hero. With my friend at Intel, Chin Ma, the pair, so Stanford, Intel, they're so close together, right? Chin Ma was a very good friend of mine. I was so far away. I was at UC Santa Barbara, so I did not involve in the final solution. The final solution turns out to be very simple. They say, okay, so when you make your film, right? So that then they glue another chip on top, just glue it instantly, and directly do peel test or bending test, see whether interface debound or not. So because they have a previous experience, what kind of load causes fracture? If this load causes fracture, that won't pass 3 months test. If you can pass this test, you will pass that test most likely. So then they turn this thing very rapidly. The moment you turn the knob, this morning you turn the knob, the afternoon I do a rapid test for you. And you already know it works or not. So now I simplified a little bit. So in order to relate the fast test, what we call accelerated test, to the real test, you need to understand mechanics well enough. So made some contribution to these guys' final solution. So that shows me how mechanics actually is used, really literally save huge amount of money for Intel, and also made colleagues at Intel understand, see how academic research could actually help. So for many years, I had a steady stream of support from Intel, not only in terms of money, they provide some money, and also steady stream of just good problems they feel important and they couldn't solve immediately. They just have we had a monthly meeting. You asked me how to identify problem. I use other people to identify problem for us.
I would like to thank you for this example, very concrete and also clear for students and myself how you can solve problems.